Hey everyone, welcome to the final video for Math 9 ASI. This is our 12th video. Today we're just going to be going over increasing and decreasing functions and concavity and how we can find that using the derivatives that we've been learning about, and then how we can put everything together in order to sketch graphs. Okay? So first off, increasing and decreasing. So if f is a continuous function on a closed interval ab and is differentiable on the open interval ab, then if f prime of c is greater than 0 for all c in that open interval ab, then f is increasing on the closed interval ab. So similarly, if f prime of c is less than 0 for all c in ab, then f is decreasing on ab. And if f prime of c is equal to 0 for all c in ab, then f is constant on ab. So this is just saying if the derivative is positive, then we know that the original function is just going to be increasing. If the derivative is negative, then the original function is decreasing. And if it's 0, we know that it's constant. Either at a single point, we know that we get like a peak. It's like constant for that single point. Or you might have the case where it's like a flat straight line for a little bit. So either way, the function is constant. Before, we weren't entirely sure how we can determine relative extrema. But using this information, we now have a strategy, and we call this the first derivative test. So if the sign of f prime switches from positive to negative at c, then f of c is our relative maximum. And if the sign of f prime switches from negative to positive at c, then f of c is our relative minimum. And if the same as before, if the sign is the same before and after c, then f of c is not a relative extrema. Okay, so taking a look at an example of that. Here we have f of x is equal to x squared. And we see that we have an extrema here at 0. And we see that it's a minimum. And so if we look at our derivative, f prime of x equals 2x, then we see that at 0, we're shifting from being strictly negative to strictly positive. So if we're switching from negative to positive, then we know we have some sort of minimum. And this is a simple case. You might check this on a more complex graph. Because here this is just an absolute minimum, which is easier to find, but you might have a case where this is relative and it's not quite as easy. And conversely, we have g of x is equal to negative x squared. Same thing, but now we're just kind of upside down. And at 0, we have a maximum rather than a minimum. And so looking at the derivative, g prime of x is negative 2x. We're shifting from positive before 0 to negative after 0. So positive to negative means that we have some sort of maximum. Okay? Next up, we have concave up and concave down. So let f be differentiable on an interval I. F is concave up on I if f prime is increasing over I. Also, the same goes for if f double prime, or the second derivative, is positive over I. And f is concave down on I if f prime is decreasing over I, or if the second derivative is negative over I. And it has no concavity on I if f prime is constant, which is also if f double prime is 0. And a point of inflection is a point on a graph f where the concavity of f changes. And the point c, f of c, is a point of inflection if the second derivative, if f double prime of c equals 0, or if f double prime is not defined at c. And we can use this concavity to determine relative extrema too. So if c is a critical value of f and f double prime of c is defined, then if f double prime of c is greater than 0, if it's positive, then we know we have a local minimum. Or if the second derivative is negative, then f of c is a local maximum. And I'll show that right now. Using the same examples, but this time we're using a second derivative test. We have f of x is equal to x squared. We see, again, we have a minimum here. And here our second derivative is positive. It's strictly positive. It's just equal to 2. So that means this whole parabola, x squared, is always concave up, which you can see because it kind of has that like upwards facing like cup, I like to describe it as. And because it's positive here where we have a critical point, then we know that it must be a minimum. If it's concave up, it makes sense that this is going to be the minimum, the bottom of the cup. And again, conversely, we have negative x squared. where we're upside down, and we have a maximum here at 0. And we see that our second derivative is just -2, so we're always negative, meaning the cup's upside down. We have concave down, and our maximum here is basically like, I guess, the bottom of the cup, but we're upside down now. So this is our peak. So this is a chart that my high school teacher, my high school calculus teacher, Mr. Bonnier, provided for us. I think it's pretty helpful to basically sum up everything we've been talking about the relationship between a function f prime, and f double prime. So it just kind of shows like, oh, if it's positive in f prime, then we know we're increasing in f, or if it's negative, we know we're decreasing. And the change from one to the other implies relative extrema. And the same thing for relating the second derivative. So if this is positive, then we know f prime is increasing, and we know f is concave up. And the same for negative, decreasing, concave down. And a change in any of these to each other implies points of inflection. I just think it's a nice summation of everything, and it's good to have on hand if you ever forget these kinds of relationships. Okay, so lastly, let's put everything together, and we can kind of make a simple algorithm for sketching graphs using everything we've learned. So step one, we want to determine our domain. So like, for what x does our function exist? Is there any points of discontinuity? Is there anywhere where our function just doesn't exist anymore, like somewhere where it can't be? Stuff like that. Step two, we want to determine where the graph intersects with the x-axis and y-axis, as well as if there are any horizontal asymptotes. So finding intersections of x-axis and y-axis is pretty simple. We just want to see for x-axis where y equals 0, and for y-axis where x is equal to 0. And for horizontal asymptotes, that comes in handy when we're sketching it. We would know like, oh, okay, so we don't have to draw any points above a certain line, that kind of stuff. Step three, we want to determine critical values, maxes and mins, inflection points, and vertical asymptotes. And then along the way, we want to draw diagrams for determining where the function increases and decreases, and where it is concave up and concave down. Just kind of keeping track of, over what intervals are we increasing and decreasing, and over what intervals are we concave up and concave down, just so we have all the information on hand for when we're drawing it. And with everything that we found, we can sketch the curve using this information, and we can connect our known points. But you want to be sure to keep track of concavity. So if you have a point here and a point here, you don't want to just draw a straight line if you know it must be concave up. You want to just kind of like, make a little cup shape, or if it's concave down, kind of like that, All right, I think that basically covers everything. Again, as always, please sign in down below if you can. You can ask questions. I don't have any more office hours after this, unfortunately, but you can still email me, and I'll try to get back to you as soon as possible, or leave a comment, and I'll try to answer that. Yeah, hopefully you found these videos helpful. And thank you so much for watching. I hope you guys have a great summer, and you guys are staying safe. So thank you.